Look at a dense system of linear equations, with multiple variables interacting simultaneously across several different lines. To make sense of this, we first pull away the variables, the x, y, and z terms, and isolate the raw numerical coefficients. This textbook excerpt defines a matrix as a rectangular arrangement of these numbers. We organize our extracted coefficients into an m by n grid, where m represents the rows and n the columns. Next, we stack our extracted variables vertically to create a single column vector, which we call x. The constants from the far right side of our equations form a second column vector, labeled b. Looking at this system of linear equations block, you can see how these distinct parts combine. The chaotic list of equations is condensed into the singular expression a times x equals b. By compressing those tangled equations into this structure, we trade tedious line-by-line algebra for geometric manipulation. The variables are isolated, and the structure is set. Our objective is to isolate x. In standard arithmetic, if you have a times x equals b, you simply divide b by a. But applying a standard division operation to a multidimensional grid is mathematically impossible. You cannot divide by a matrix. To bypass this limitation, mathematics requires a workaround, the multiplicative inverse, denoted as a to the negative first power. Isolating the variables requires a deconstruction of matrix A's internal elements to synthesize the inverse, the only structure capable of neutralizing the original matrix coefficients. The manual outlines the first check, calculating the determinant, defined in point 4. This scalar value measures how much the matrix warps geometric space. Notice point 6. If the determinant is exactly 0, the matrix is classified as singular. A determinant of 0 means the geometric space has flattened. The matrix has lost its structural integrity, making an inverse impossible to build, and indicating the system lacks a unique solution. Therefore, only non-singular matrices, those with a non-zero determinant, possess the necessary integrity for an inverse. The determinant acts as the ultimate gatekeeper before we spend any effort taking the matrix apart. With a non-zero determinant confirmed, we begin the physical deconstruction of the matrix grid, targeting one specific element at a time. This rulebook defines a submatrix as what remains after deleting specific rows or columns. For our target element, we completely erase its intersecting row and column from the grid. According to point 3, we calculate the determinant of this smaller submatrix. This is the minor. We then apply a positional sign rule, -1 to the power of I plus j, dictating whether we multiply our minor by positive or -1. Multiplying the calculated minor by this alternating sign gives us the cofactor. We execute this exact extraction, calculation, and sign switching process for every single element across the entire original grid. These newly calculated values snap into place, forming a brand new configuration. This cofactor matrix represents the collected determinants of every subgrid within the original matrix, providing a new grid of localized scaling factors. We need one final geometric manipulation to reorient these dependencies, the transpose operation. We physically detach the horizontal rows of our new cofactor matrix and rotate them exactly 90 degrees, locking them in as vertical columns. This text defines the transposed cofactor grid as the adjoint matrix. We scale this adjoint by the reciprocal of the determinant to yield the definitive formula for the inverse matrix. A inverse equals 1 over the determinant multiplied by the adjoint. By methodically tearing the matrix down into minors, calculating its cofactors, and reorienting the structure with the adjoint, we forge an algebraic division tool that bypasses the rules of standard arithmetic. Now we return to our unsolved master equation, a times x equals b. We take our newly forged inverse matrix and pre-multiply it against both sides of the equation. On the left side, as the inverse matrix multiplies against the original matrix A, their opposing structural properties collide and dissolve. This document defines the exact result of that cancellation, the unit or identity matrix, characterized by its diagonal line of ones. Multiplying this identity matrix by our variable vector x simply leaves the isolated vector x. The identity matrix functions exactly like the number 1 in standard arithmetic. It neutralizes the complex coefficient matrix from the left side without violating algebraic logic. The structure is cleared. We turn to the right side of the equation. where the inverse matrix is now multiplying against the constants vector b. The horizontal rows of our inverse matrix sweep through the single vertical column of b, executing a directional dot product calculation. As this non-homogeneous equations rule confirms, this final operation compresses the structure down to a unique solution, equal directly to x. The numerical values in this final column map 1-to-1 with our original variables, giving us the exact answers for x, y, and z. By substituting standard division with the inversion process, we resolve the system through a controlled sequence of matrix operations. This methodical approach handles high-dimensional variables with exact algorithmic certainty.